Cool. So we're getting into sort of the core of modern music gen system. And likely you'll figure it out when you work with music gen and models like that usually are based on this kind of latent-based music generation model. Cool. So before we jump into what is latent music models, we want to talk about one thing that's, sort of broader than just music generation, which is called neural codecs. And basically, the key idea of latent-based music generation, you can think about it like, well, do we want to generate waveform directly, as we talked about on Monday? It doesn't really make much sense, right? Like, think about you're generating 44.1 samples per second. Does that even make sense? But we've have so many this kind of codec like MP3, M4A, AAC, and that's like a sort of like a more compressed representation of music and audio. So the whole idea of latent-based music generation is that, well, can we figure out a more compact, more efficient representation? And now we are generating music in that representation, and later we decode it back. So that's the whole idea behind latent-based music generation, but also, image generation, video generation, everything you've seen sort of like stable diffusion, latent diffusion model, some of the, VQVAE, some of the tokenizing everything kind of narrative are all surrounding around this neural codec idea. Even Bluetooth, when you are connecting with your earbuds, it's not sending 44.1 samples every second. It doesn't make much sense. So it's actually encoded into something and then transferred to your earbuds. So, for Bluetooth, it could be SBC, the early time Bluetooth, AAC, aptX, and LDAC. These are some of the more, advanced, Bluetooth codec. But think about when you are transferring files, it could be, MP3 or, even in the Zoom setup, these will be, MP4. And basically you record and you have those you have those recording. You are not sending the raw audio to the cloud, but you are sending something that's compressed. And then you return it back. So the idea of neural codec is basically similar to traditional codec. So, an MP3 codec is basically, well, you have some audio, turn it into some bytes or, numbers that represent the original file. And it's like much, much smaller in size. So much more compact and efficient representation of the same audio. So, you could think about one way to make it more understandable is think about, spectrogram in the very low resolution, just like the one we saw in the last PA, that the 64 by 64 mel spectrogram, it doesn't make much sense, right? It's like too tiny in size, but still it captures something. So these MP3 or, the traditional codec is trying to optimize the way how human brain or auditorial system work. So we reverse engineering to capture those important information and use last bits for those frequency that we are not that sensitive to. So neural codec is just another way to think about this. Now we are just using the neural encoder, neural decoder to do this. So this actually doesn't have to be neural codec. This is essentially just an autoencoder, right? So basically, you're just replacing the encoder and decoder with some neural net. So this is the idea of neural codec. The internal this things it can be discretized. It can also be continuous number. So it doesn't necessarily turn something into a lower dimension, but it usually turn them into lower dimension, but you have to quantize it so that it becomes real codec. But in the in the context of latent-based music generation system, we don't necessarily need to quantize the internal the latent vector in the middle. So the things is actually called latent vector. So latent means hidden, kind of. So this is like one of the hidden layer, and this is one of that latent vector in between. But also, VAE and GN, those, Z that we keep talking about, we also refer to those as latent vectors because we are thinking about deep latent variable models. So this is essentially just autoencoders. So once again, autoencoder is just a neural network where the input and output are the same. So technically, neural codec is just a type of autoencoders. So you've seen, autoencoders can do a sort of like this reconstruction examples. So, it's sort of capture the most important or more repetitive or, a data-driven way of thinking about compression and, reconstruction. Like what are the most important part of the inputs that we should capture across our data set so that we can reconstruct the original sounds as faithful as possible through a data-driven way to look at your data to think about what would be the best way to represent, to compress this data set. So there's a bunch of models, but if you look at those, they usually look alike. But basically, the idea is that you want to turn like a waveform all the way towards something much smaller in size, and then turn it back. So we won't go into details, but this is kind of the encoder waveform and a lot of like convolutional layer and all the way into something in lower frequency. So this is like 24 kHz, but all the way until that some vectors that happen 75 hertz. So you turn sort of, I don't know what this ratio would be, 24 thousandths over 75. So I don't know, 300-ish compression rate in that idea. And the decoder just do the opposite way. Just turn the things like a vector happen every 75 hertz, but that correspond to 300 samples. So this is also similar to the idea where we talk about in vocoder, where each slice in your spectrogram correspond to a certain number of samples in the audio. And this is just another way to look at it. But basically, these encoders, you can look at those, but it's basically just doing a lot of like convolutional neural network and just playing with the size. And at the end, you are training these with the reconstruction loss. So in terms of codec, not in terms of the way how we are using it in music generation system, like latent-based music generation system, but if you're wondering how you can actually turn this into a codec, is that, at the training time, you basically grab an audio and you encode it. And in the middle, this RVQ actually quantize the vector into several possible centroids. So think about, in the middle, this latent space is like 64 dimension or, 64 bits of information that you can put in that vector. So it will be a space. But these things you can actually find clusters within that space. And you are just grabbing those clusters as the centroid of certain samples. So in that sense, you can actually quantize these information. So what's being used here is additional, there's a discriminator on top of the reconstruction error, the reconstruction loss. So think about reconstruction loss. We talk about it, reconstruction loss on waveform doesn't really make much sense. But you can actually use SATFT to turn that into SDFT and compute reconstruction loss on spectrogram, then it make more sense. But here they also use this adversarial loss because the adversarial loss is so powerful in keeping the audio clarity. So adversarial loss usually serve as a way to improve the sharpness of whatever model you're doing. Image generation, the same. Without, adversarial loss usually look a little bit blurry at the borders. But once you add adversarial loss, it will do really good. Like think about the hairs. Those are things that without adversarial loss is very tricky. Because if you think about the hair, it could be any direction. And if you are optimizing it using like, mean square error, usually they will just smooth out. It's just nothing. Cool. So, this can be actually used as a codec because, if you break the things apart that, you encode it into something and then you can quantize it, then, what you're sending is just the quantized information to the receiver and the receiver can turn it back. So this is actually a very active field. Lots of, in the future, maybe we will see more codec in this format where the idea is that Is bandwidth the most important thing? Or, nowadays we have edge device. Think about our earbuds. It's like getting so powerful that we can run noise suppression on on device on your earbuds on the fly. So it could potentially just synthesize the sounds back on the fly in your earbuds with a very low latency. So, people are thinking about this, but also there's would be, think about Zoom meetings. You're sending a huge, video and audio information, and sometimes the network will be very bad, unstable. Then, with the lowest bit, bandwidth, can we still try to sort of like alleviate the burden from the networking or bandwidth to your laptop to reconstruct it back. So it's just like balancing which computing resource are allocated through the bandwidth or on your laptop doing all the work to reconstruct it. Questions? This is actually similar to how traditional telephone works. So, the landline is actually just resynthesizing your information, your sounds, rather than, just recording all the tiny, fluctuations on your waveform. It's actually doing some resynthesis. So, the good old telephone. There's also some other models, but I won't go into details. In codec, this is a better version built on top of the SoundStream. And discrete audio codec is another one. But these codec, I will show you, but they work very good in terms of their, like their compression rate, but also the reconstruction quality. So just to show you how that might look like. So this is sort of the idea when people are thinking about this codec. So usually at the x-axis is like how many bits of information you are sending. So in the lowest bandwidth thing, think about unstable network. And here is like if your network is more stable, or you have more bandwidth and you can send more information per second, then you can actually achieve a better score on the audio quality. So at the y-axis, you have the audio quality. Of course, the original sound would be the best. This is in codec. This is discrete audio codec. So you can see at different bit rate, meaning that the same file size or the same bandwidth there you are using, it actually achieve a better better audio quality. And the y-axis, the x-axis is just the compression rate. So the lower the bit rate, meaning that you are compressing it a lot. So, whenever you see this kind of plot, that basically you want it to be either, high quality, you want it to be at the top left as possible, high quality, high compression. And at the bottom right, it's like low quality, low compression. So it doesn't do a lot of things that you can just send the original waveform. Anyway, this is just audio codec. So how does that connect to the latent-based music synthesis? But the idea is just similar. So the idea is just that, well, do we really want to generate music and audio as waveform? It doesn't make much sense. You are generating so many numbers in 1 single second. It doesn't really feel right. So the idea of latent-based audio synthesis is just that can we sort of first turn this waveform into some latent representation. In this case, think about MP3, think about whatever in codec, discrete audio codec, but turn it into something else. Now our goal is to generate those things in the middle rather than generating the original waveform or generate the waveform directly. So this is, of course, we need another deep learning model because even the thing in the middle is just not make much sense. So these are the first steps if you want to train latent-based music generation model. So first you train an autoencoder where you basically train a codec basically. So you will have a bunch of different file, of course, and you will get a bunch of different version of that latent vector. And of course, you will reconstruct it back. And the idea is you will train these two things so that it reconstruct as faithful as possible. So now once you have this, pair of encoder and decoder, basically you will just grab your whole data set and turn them into different that animation. So basically you will turn all your files into that latent representation. So think about you have a bunch of WAV files. Now you turn that all into MP3 files. And then, forget about the waveforms. We look at the MP3 files. So the idea now would be this is the thing that we've been talking a lot about, train the latent generated models, GM, VAE, transformer, whatever models you like. But now we just want to try to use some of these deep generated models to generate those latent vectors. So that's the idea. And once you have those, you already have the decoder, you know how to turn it back. So grab those things you generated, then you can get the audio back. So, it sounds perfectly nice, but that also make it more complex of these kind of modern models. And that's also the reason why, nowadays these are getting, more commercialized, and it's very tricky to train it from scratch. But still, hopefully we will see more foundational model that we can use. Some of these autoencoders, because it's act more like a reusable component. So you can find a lot of these models, but if you want to find the generation model, it's much trickier to get it. And that generated model also depends on the codec. So you are generating into a certain codec. So it doesn't reusable to another codec. But anyway, these are the 4 steps. First, you train an autoencoder. So think about you train a codec, like a neural MP3, and you turn everything into that neural MP3 representation. Now you want to train another latent generated model to generate music in that specific codec that you train. And finally, you will just decode the latent vectors back to the audio. So the training components of these are just 2. One, you need an autoencoder. That's sometimes referred to codec, sometimes even referred to vocoder, sometimes tokenizer. You see some people call it audio tokenizer, because you are sort of trying to turn the things into some embedded vector. So some people also call it tokenizer. And you will train another latent generated models that basically turns some random noise into reasonable latent vector. So for inference, once you train these models, you are not training this, so you have this frozen mark, meaning that they are not being trained anymore. In this case, the fire usually just suggests that it's under training. But inference time, it shouldn't be too tricky. You grab something from the random distribution, just as we see in the GN and the diffusion, VAE things, and you generate some of the latent vectors, and then you decode it back. So that's a high-level idea. Questions? Sounds very ideal, and then later you will see how tricky it is with all the real-life models. Cool. So that's the high-level idea. Now you sort of get a sense how these different components are, and that's why some of these GitHub repository is usually very messy, because you have so many different components at the same time. But this is one of the first sort of latent audio synthesis model. So here, one thing to notice is that we oftentimes looking into text-to-music synthesis nowadays, because generating random music without any control just doesn't make much sense. It's that, well, give me some music and then you get something, but why? We do want some control to some extent. So people nowadays are very exploring a lot in text-to-music synthesis. Part of the reason is just that there's some way we can sort of like build these kind of data set, just like how we get the image caption data set. So, go to Wikipedia, there's an image, there's usually a caption underneath it. But for music, we can still, look at some of the stock music data set. So, Adobe stock music, Shutterstock music, I don't know, they have music, but anyway, there's different kinds of stock music providers where you have stock music, but you usually will have a caption or a short descriptive text to describe so that you can search and query for those stock music. So there's some way we can get this kind of data set, and that's why we are exploring a lot of text to music synthesis. Of course, that's not the end of day. Of course, text is very limited, but at least we can get started with this. So audio gen is one of the first model that people think about. As you can see from the name, is the parent or the mother of MusicGen. So AudioGen came out first, and then and then they retrained AudioGen and turned it into a music version called MusicGen. But AudioGen is the first model that people are looking into this kind of idea to generate audio or music that we care about using this kind of model. So this is the figure you will see, in the paper. But anyway, if you break it down, the basic idea is, something similar. You have a bunch of audio, you have an audio, and you turn it into something that they call audio tokens. That's also why some people talk about these codec as tokenizer, but basically you want to turn it into some numbers or some indices, so that you can reconstruct it. But basically, this is just an autoencoder. So once you have this autoencoder trend, then you just put it at the bottom and the top. So what you are trying to do now is, think about text to audio generation. So essentially, you have this text, and what you want to generate is the audio tokens in the middle. That's the idea. So you grab a bunch of files where you have, a dog is barking in the park. You have the audio. You turn this audio into some, tokens that you can later turn it back. But now the idea is that how do you go from this text to this token? So the idea behind audio gen is that, well, this is a translation idea. Like, think about German to English translation. Think about this is like English to alien language. This doesn't make much sense if you just look at it, but it could be some alien language. So we can actually reuse some of these translation models, machine translation models to do it. And one of the iconic machine translation model is basically Transformer, right? So we talk about Transformer, we sort of like simplified it a bit into decoder only Transformer, but the original Transformer, as I talk about, the reason why people are interested in that attention thing is because in machine translation, it doesn't always sequentially match the attention. Sometimes there will be reverse, sometimes it will be referring into different word-to-word translation. But basically, this is just grabbing the transformer idea. You will have another text encoder, but basically this whole thing is just a transformer that's doing that job. So you will have the English coming in, and then you do sort of like think about transformer that you are keep generating the next tokens. So the model just see a dog is barking to the park, and then some alien language like blah, 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 blah. And what you want this model to learn is that whenever you're given a dog is barking in the park, it knows what that blah, 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 blah will be. And then if you have a cat meowing, I don't know, in the classroom, then you will get the other blah, 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 blah as your output. And that's basically the idea. And one of the core reason why it's working is because it's trained on sort of like the largest data set back then, 4K hours with text and audio pairs. And it's actually very computationally intense. I think they use 64 A100 GPUs and train it for 2 days or a week. I think there are several versions of that, but it's like crazy computational intense the first time when people think about it. So these are the outputs that what it sounds like.
Also, that's like sorry. No.
So you can likely guess like what the data set would be. So a lot of these are actually based on the sound effect data set. So think about film sound design. This is also a very active field. Premiere Pro already port a lot of these kind of models in Premiere Pro. Now I forgot what his name is, but Jan sound effect likely. But nowadays you can also look into Premiere Pro, and then if you want to add a sound, you just click on the timeline and then you just type in what kind of sounds effects you like, and it will generate it for you. But also, some very exciting things. I love films. That's why I'm very excited about this. Is that, looking into the video so that you can actually look at the video and then just know, well, there's a dog running by, then you can potentially just click it and then you get the sounds right away and contextualize in that specific setup. So there's a lot of thing of going on in this sound design world. And, think about music more broadly. Sound design nowadays is also part of music creation sometimes. It's oftentimes very hard to distinguish, like in electronic music, some of the pad, some of the effects, like during the transition between boundary, it's just kind of tricky to define whether it's a sound effects or music. And also, in more than film scoring, usually the idea of music and sound just blur together to create that immersive experience. But anyway, this is the first thing that people try. The idea is that, well, with these inputs, it wants to translate into some alien language that can be decoded back. Think about these language into some MP3 bytes, and then those MP3 bytes, how to decode it back. So the idea is just translate to MusicGen. So MusicGen is also one of the first model. I think the last time I checked, the website is done. Let's check it out again. So this is MusicGen. They used to have a music. They used to have a Hugging Face, but last time I checked, it was done. But they used to have a very nice, Hugging Face space. It's more like, you can check their code. Hopefully if you can fix it, it should be good enough. I guess it's just some version issue on the NumPy things. But anyway, that's also part of the reason why a lot of people are using MusicGen, because it does provide some, collab and Hugging Face code for you to get started. But anyway, MusicGen is just audio gen for music. For most part, it uses a better, codec. In codec instead of SoundStream for audio gen. So improvement on the codec. But also more interesting is that they actually use 20K hours of licensed music. The biggest chunk, I would say not the biggest chunk. I would say the high quality part of that is private, unfortunately, the internal data set. But they also have, Shutterstock, stock music, Pond5 stock music for most of their data. So they likely pre-train the model on these and then use the internal data set to improve the quality of that, because these are stock music. We can listen to some of their generation. It used to have that, interactive things that you can prompt, which is more fun. But anyway, good, check it out. So grand orchestral arrangement with thunderers, percussion, epic brass. Let's listen. But this is better than I thought. I think this is the updated version. They also have the stereo version of that. Cool. Music LM is the one by Google. Refusion is another company working on Refusion, and Mosaic is another two music startups. We could also check out electronic track, catchy beat, and groovy bass. Smooth jazz. Acoustic folk song. Punchy double bass. Anyway, you can check it out. And regarding the melody conditioning things, this is here it is. So you can actually print this model with some melody as input to generate the sort of like accompaniment or anything other than vocal. At least their original code is not working as good as these likely, but we can take a listen. Okay, rock song version. Thoughts? Okay, they likely have updated the model. I think they now are using this audio crafting. So I think so basically Facebook just compiled these models into one big chunk of code base. So you have a bunch of those, music audio gen, we talk about it, music gen, but also encoded as part of that. Now they also have multi-band diffusion. That's even more encoded compatible decoder using diffusion, and there's a lot more. There's also this style transfer thing that potentially you could look into if you want to do style transfer, music gen style, and everything is in this AudioCraft data set. Not data set, I mean repository, and that's part of the reason why the original music gen repository is no longer maintained. Well, let's listen to the GitHub one. Well, not bad. So, the idea of these conditioning model is just adding more context to the model. So, in addition to, an energetic hip hop music piece, blah, 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 you add more context to that. So think about, in this melody case, where you just add more, the melody, think about additional prompt to ChatGPT that, well, this is the melody that you want. And the idea is still, well, the model will generate the rest of those, music in that latent encoded representation or an alien language as we talk about it. Cool. So this is like music gen, likely one of the few open source model that you can still play around with. And MusicOM, this thing is in Google Verse, as we joke about. So Google didn't open source it, but it's pretty cool to look into what's going on with their way to do this. So basically the same idea that you have sound stream, but you can also train an audio encoder, but there's additional two models that we won't necessarily go into details. But basically the idea is that we want to do this course to find generation. So first we grab the text, we want to generate something middle layer idea of what this music is all about. And then later you turn that into the real token that you are generating, and then you turn it back to waveform. There's also this Mulan things that we will talk about it later. So this is a different way to think about text to music generation. Now you are basically training a model, a contrasted model that we will talk about later, but basically you are sort of like scoring how close your audio and the text are, how close they are, how, are they, relevant, or text to music correspondence modeling, basically. Huge data set. So these two components, the audio autoencoder, semantic representation, these two models doesn't need text music pairs. So you can actually get a bunch of songs, 106K songs, 8.2K hours. Text music correspondence, you do need text music pairs. So they actually grab a bunch, 370K hours. So what's contrastive model? So as we talk about here, you sort of get a hint. You have some audio, you have a text. There's like two parallel things going on. Audio network, you get the audio embedding. Text, you get the text network, you get the text embedding. So now these two things you can sort of like do query, do retrieval, or just measure how far away they are. So this is essentially kind of the way the most the paradigm nowadays to do text to music generation, but also text to image generation, but also different things. So this thing is called contrastive language image pre-training, which is called CLIP. So likely you might heard of it somewhere else. But the idea is that, well, now we are training a pair of encoders. So we are getting into very recent stuff. So if you check it out, it's like 2021 in ICML. So it's a very recent stuff. But the idea is that, well, you have a data set that's like text and image. So you have the image of a cat, and you also have the text CAT. So the idea is that, well, you grab the cat image and then you send it to some image encoder, you will get a vector of that. And then now you have the CAT, the text, and then you send it to the text encoder and you will get an embedding for that. Of course, usually we are not talking about cat this simple. Usually it could be an orange cat, like cute orange cat looking at you, stare you in the eyes. So something like more descriptive. But in this case, just assume that's just CAT. Then now you have another image, of a dog. Then you have the dog image. You send it to the image encoder. You get the embedding for that. You have another, DOG as the text, and you send it to text encoder. You get this, vector. So the idea of contrastive modeling is just to make close these two things. So you want the image representation of the image of the cat and the text representation of CAT to be as close to one another as possible. And the same for dog. So now you essentially train this kind of model so that it knows that, this image encoder and text encoder will throw the same idea to the same place in that latent sort of semantic embedding space. But everything else you want to make farther away. So, the image of cat, the image of dog, they should be further away. And, image of cats and DOG, the text, of course, they have to be further away. So that's sort of the idea of contrastive learning. So the whole idea here that, you want to put two things that's semantically close to one another and, everything else. So this is why it's called contrastive learning. So you are sort of like using that contrast to train these kind of model. So the only correspondence you are doing is the pair, image text pair that you want to model. Questions on this? So essentially you get two models. That's one of the most confusing things. You actually get a pair of encoders, but they throw stuff to the same space. And if they are semantically similar, like in image and text, then they will be thrown to the same point. But if they are not correct, not relevant, then they will be thrown to different places. Cool. So now you can get a sense why this can be useful in text to music generation. So, if you have the text, you have the music, then now you generate some music, then you do know that how far away you are generating that music. Are they close to the text that you have as the input, or are they further away? So there's some supervision signal that you can model the text music alignment, between the input text and the output music that you generated. So basically, the idea of contrastive learning is just learn a shared embedding space for images and languages. So language music pre-training is basically the same idea. We have some music, fashionable lo-fi hip hop. This is usually the kind of caption you get in these stop music data sets. Dreamy, fantasy, orchestra. So you could get some of like text like this, but the same idea. Music encoder that will turn the music into some vectors. The text will be some vectors, but the idea is that this audio file and this text should be thrown to the same space in that embedding space. So you just basically learn a shared embedding space for music and language. So that's essentially how Music LM is kind of working. So the idea is that, well, you have the audio. So you grab the audio and you use this Mulan model is basically this contrasted model. So you take the music encoder here and you turn this input audio into the Mulan encoded vector. So this things is the Mulan tokens. So those are just vectors that capture the semantic representation of the things. So think about, you have this audio, but you turn it into some representation that captured this fashionable lo-fi, hi-fi idea. So that's essentially what you have as the input. And now you want to generate this middle layer representation called semantic tokens. But think about it, it's just like where we get some audio and we go through one of these kind of like big model and we want to generate a sort of like intermediate layer representation. So this is to some extent just like think about MP3 sort of, but not essentially codec, but something even more higher level than a codec. And the last thing is the things that we know about. This is the codec, and we want to generate the exact output codec things that we want. So you can actually just jump from Fulan tokens all the way to acoustic tokens, just as previously in AudioGen. But in this case, Music.ly just divided into even one step further, that there's additional middle ground between when you jump from the text all the way to the tokens for your codec. Anyway, they trained it on the big data set, of course, 5 million songs, 280K hours, so huge data set. But once you train this kind of model, now the trick lies in here. So as we talk about here, where you grab an audio, like music, and then you use this Mulan model to turn it into the audio tokens, right? So the clever thing about MusicLM is that now you have this text. Now you have a pair of text and music encoder, right? They sort of throw stuff to the same space. Now, basically, you grab that text encoder of Mulan. So Mulan is a pair of text and music encoder. So you take that text encoder, and now you throw this high hip hop song with violin solo to that space. And this space should be the same as the one that you just train your model on, right? So this model is trained on going from Mulan tokens to semantic tokens and later combined to get the audio tokens. Now, this thing's still in Mulan tokens, right? Just that now you are getting those from the text encoder rather than the music encoders. And that's essentially the reason why we can train this using without any text audio pairs. So text audio pairs is only used to train this Mulan, but at this stage, we don't need text audio pairs anymore. And that's why they can scale it to 5 million songs. So basically, you train your Mulan, that contrasted text music model that knows the correspondence between them on the smaller data set so that it captures the understanding of the relationship between language and music. But now you scaled it up in this case where you no longer need text audio pair so that you can scale it to 5 million songs and 280K hours. And so that's essentially how music alignment is being trained. So now you grab the text, you turn it into the same Mulan tokens. Now you generate that semantic tokens because you know how to do it during training. And now together combined, you get the final outputs out. So, this is essentially a very clever idea where you no longer need these kind of, text music pair at this stage once you have the Mulan trend. Oh, good. So this has been constantly used in a lot of different ways. So this idea is actually not first explored in MusicLM. So have you heard of like DALL-E by Google? Is DALL-E from Google? Yeah. Is DALL-E from Google or from OpenAI? But anyway, DALL-E 2 is essentially using this idea. So DALL-E is basically, text to image generation. So they basically use the same idea because we have clip for image, similar to how we translate it into, text music models. Oh, good. Cool. So once again, nowadays, things are being highly commercialized. a lot of components, but in this case, this music LM is not just one single model, it's actually a bunch of models that, these are the three components. But on top of these three components, you also need these two mapping from the, Mulan token to semantic tokens. So it's actually 5 models. So you want this semantic modeling. This is also a transformer model. This acoustic modeling is yet another transformer model. And then you need these 3 models. So it's essentially 5 big models at the same time. So, this is like a sort of like an AI, I don't know, nowadays become more commercialized. This is like an AI infrastructure that you have multiple models doing their job and how you gear them, engineer them to work together toward your goal. Cool. Let's listen to some of the example. You can actually try them for free. For now, I don't know when they will block it. Sign in. Just use my Umish account. Well, let's just do this. Soulful jazz for a dinner party. So this music LM, now it's branded as Music FX, but basically at the back end, it's just Music LM based model. Well. Kind of slow. Anyway, this is Music FX. But what's more exciting nowadays is about this idea of like Music FX DJ, the streamable. Like it's always. Isn't it the same motif? I don't really like it actually. Let's find another one. Any idea? 80s. You want more condition? With drums? Let's do it. Anyway, you can play with it. We might wait for 10 seconds. But this is like the streamable things that I would just show you later next. But this is pretty cool. But the same idea, now you are generating music on the fly. Every 30 seconds, it will generate the next 30 seconds of that. Based on a similar model, but of course you have to retrain it so that now it's sort of like doing continuation on the fly rather than generating this like 30-second standalone chunk. Well, not bad. That's fine. Laptop sound. Let's wait for it to fade out. I never figured out what's the cost of that. Somehow there used to be 3 totally different versions of that, but now it's just 3. I don't know what's going on. I think there's something wrong with this thing. Usually there will be 3 versions of that. They usually doesn't sound alike. But anyway, what I want to show you is this Music FX DJ, which is pretty cool. Basically, you can just train on the fly and think about you like a DJing that you can swap between these prompt so that you can think about these as, you can map it to like a DAW where you can or a knobs or a slider that you can mix on the fly. So if you look at this, it's just like keep generating the next 30 seconds. And now if I do this frantic percussive viola, another switch. That's more. You can imagine that you can create a smooth transition over time I don't know. I feel very excited about this for gaming in the future, or I don't know, theme park kind of things. That these music can sort of like smoothly wandering around between the boundaries of genre. And so have we seen this like Jackal Collier? Likely yes, right? At the first few class. But Jacob Collier just basically freeze. Okay, it died. Okay, our point is dying. But basically, Jacob Collier did a long session just playing around with Google Music FXDJ, which is pretty cool because he just explore how you can work with this kind of model and grab those, short chunk of idea, but try to, compose it into a broader idea, or, a more coherent idea that he want to achieve. But anyway, highly recommend. It's kind of long, but the first several minutes, check it out to see how, Jacob look into these models and play around with it and try to grab those ideas and compose into a more coherent idea. None of these music generation system is meant to just do it. It doesn't make any sense if it just do it for you. Then why do you want to make music in any case? But thinking about what are some of the ways that we could potentially be working with these models. But at the same time, one thing we figured out for the last few decades is that it's easy to just generate random music without any controls. But whenever you want to add controls, you want to add more agency for you, not for the AI algorithm. It's much more challenging. And that's also how this field sort of start with. Everything is sort of like unconditional. Well, you can generate an image, you can generate a video, you can generate some music, but who cares? But then people ask more, and then now there's a tons of very exciting things going on, so that you can have more controllable, or more interactive, or even more multimodal, gesture-based. I don't know, all kinds of multimodal controls that you can try to throw yourself into these kind of AI generated results. Um, haven't finished, but we will look into it next Monday.